Since sorry about the wobbly camera. Since making these tool holders, I've been doing some testing on the mill, and I've been getting some really variable results as to the getting the heights right on these tools. This is what I've been using. This is a what do you call it? It's a, I think people call them a puck, but basically it's for setting the height on tools. It's this alley plate is electrically isolated and connected to this blue bit of cable. So I've got a CNC router at work that we used. I used to use this with, and it's designed so you can set the height as soon as the tool touches the top of the puck, completes the circuit, and it tells the controller, CNC controller, that's where 0 is. You tell it how tall this is, and then when you take that out of the circuit, you can drive down to 0, and it sets it quite accurately. And this is good enough for a CNC router, but it's not good enough for the CNC mill. The tolerances is just too good. My little Sile mill has got a repeatability of 0.02 millimeters, which means that you need something fairly accurate. There's actually a little knobbly bit in the middle of this because I didn't turn it very well. It's made out of cheap plastic. It's the hole isn't bored square, so it doesn't. If you ran a dial test indicator around the top here, you'd find it would be all over the shop. The useful thing it does have, though, is there's a bit of sponge rubber between the two, so that if you overdrive the tool in, you've got a problem with your machine. You've got 2 millimeters of reaction time, 3 millimeters of reaction time before you squash the tool so hard into the top surface that you break it. So that's quite a useful thing. So I'm going to remake it, and this is what we're going to do. I've just shown you on the other video, or earlier part of the video, that I've let's put the light on. That I've turned the embryo shape, given it a reasonable finish, bored out the inside, and I've also fitted a piece of clear scrap plastic I had in the bottom there. So that's now curing, which it will do for another 24 hours or so. And this is a cross section of what it's going to look like. So the green is the housing, the red is the plastic I've just put in, the large bore here you can see I've done, and I got a Springham thing. There we go. Goodness knows what the hell that came out of, but I never throw old springs or things like that away, so that will fit in the bottom there. And this, I think I did a little video on where to get, or where I get some of the materials I use from. This is out of a printer cartridge for an HP printer. It's ground reasonable quality steel that's fairly dimensionally accurate at 8mm. So that's going to be the main shaft up the middle. And I've shown this with retaining a retaining plate, which I've somewhere I've got some old really thick, like 3mm thick printed circuit board, so I might use that. Up here is just a washer, and we just drill a hole through the side so we can get the cable out, and it will work in the same way as this. So the main shaft will be electrically isolated like this, so we can set up Mark III so that when you touch it, it knows the height of the overall thing. It doesn't matter what it is, as long as you know what you know accurately what that is, and then we should be good to go with a more accurate perk, or what do you call it, tool touch off. The other thing, being so long, the wobble should be really quite small. There you go, proper wobble that, which also means that it should be relatively accurate, particularly if I get the get this bore reamed out to a decent finish and the right diameter. Every feature, apart from the cutting the top off, is done in one operation on the lathe, which means, I'll go back to the lathe, which means that all of these diameter and taper, bore, inner bore, and the bore that I'll put through the plastic inside when I get that far, will all be concentric. So that means this this surface here should be exactly at 90 degrees to this this cylinder. So that means that the central touch point, when it's the top of the 8mm shaft, when it's done, should be absolutely cock on vertical, if I get it right. Because obviously if it's canted over at an angle, let's have a look at the surface plate. If it's canted over at an angle, you're going to get errors depending on where your tool touches that inclined plane, and we really want to avoid that. So let's let the plastic cure overnight, or for a couple of days. I don't know how long it'll be before I get back out here in the workshop. That's what we're making. I might not use screws here. I might actually use a I'm having a bad day, can't remember a damn thing. Might use a retaining clip in there rather than screws, because it might be an easier thing to do and actually needs less space to achieve it. So a circlip, that's the word I'm looking for, a circlip, because they're relatively easy to fix, and they're also it should be relatively accurate. But again, it doesn't matter as long as it pushes the central core, the central touch probe up, so that the washer here is flush against the and pushed solidly against the bottom of the plastic. We should be okay. Anyway, we'll see. See you tomorrow. It's the day after. This has had overnight to cure, so let's just a bit of poke. Yeah. Yep. That's in there pretty tough. Excellent. Damn it! Fuck it and fuck. Bugger it. Well, that didn't work out as expected. My drill grabbed and broke the joint. Damn it. Let's try epoxy. We'll try epoxy this time. That clearly isn't going to be good enough. Right, here we go. This is supposedly slow cure epoxy. Right then, we've had 24 hours. Let's see if this comes out. Wow. Right, today's another day, and the other day I pushed that 7.5mm drill through my insulator right down in the bottom there. Now I need to clean the hole out and ream it to 8mm so that the touch probe shaft runs smoothly in it and is insulated from the outside. Okay, let's get on with that then. Okay, that looks pretty good. Right, here we go. Well, that was 8mm. So the shaft. Oh yeah, that's pretty good. That is spot on. Absolutely spot on. Excellent. I think this is an old piece of printed circuit board, or should I say a new piece of printed circuit board. I'm going to make that round, bore this backing out so that I can put 2 of these circlips in and trap a piece of this between the 2. That should give me the connections I need. I need one insulated connection, and also this all needs to be recessed so that when this is standing up on the machine table or the surface plate, it's only touching on the outside periphery of this machined base. Then it should be, as this was all machined at one time without being removed from the chuck, it should all be concentric. And just having a thought about this, I've got a CNC mill. I ought to really cut it on the mill. Let's give it a go. I'm going to super glue. Okay, let's see if we can set this up. So let's go for a wizard. I found these wizards to be okay, but not brilliant. Select material, aluminium, close enough. Max feed rate. We could probably change that to about 120mm a minute. Not too much difficulty. Right, we need to cut a circle. Tool diameter is 3mm. Cutting tips 3. Calculate chip load. Calculate speed and feed. Yep. We don't need flood. Continue. Right. The centre is 0, 0. Circle diameter is 26.6. 26.6. Depth. Another depth. I need to measure how thick this circuit board is. 1.7. Do we do that? 1.7. Yeah. 1.75. There we go. So we should have 0.05mm deeper than we need to go. Pitch, rapid height plus step depth 1mm. Yeah. Postcode. Exit. I'm going to dry run this to start with, so I'm going to G0 Z 50. That's moved the head up 50mm out of the way. Now if I 0 that, we should be able to run it. Right, back to the mill. Okay, cycle start, here goes. This spring has to be insulated from the outside, so you can either put the plate in upside down because the other side is bare fiberglass, or you can mill round and give it a little pad to sit on. Right, looking good. Okay, a little bit of a polish up on a bit of emery paper, and we have our insulated plate. Let's try it. Spot on. Let's put this in. There we go. Well, chuffed with that. Good stuff. Okay, next up is just to resurface the top of this. I want it to be about 80 tall. So, yeah, I think looking at that, I mean, none of it's critical. I think I'll just face this off until I think it looks good. Back to the lathe. Okay, not too shabby. Oh, that's lovely. Very smooth. The shaft that is going to go through here is handily already comes with a roll pin through the middle. So what I'm going to do is just chop it through there, and then we'll do a trial assembly. That's the plunger shaft. On the plunger shaft we put one of the original bearings. Then shove it up the hole. There you go. There's a spring. To swing him out over here, I think. Here we go. There we go, that's the bottom. There we go. And that should be, or should, end up being quite repeatable. So, just check we're at 0. We're at 0. And let's come up to 80. There we go, lock it off. Now I need to disassemble it, and you probably can't see that very well on camera, but I've scribed a line all the way around it at 80mm tall. So now I just need to dismantle it, cut it off, face it off, come back here, measure it, work out how much more I need to take off, and then rinse and repeat until I get it down to, when it's fully assembled, 80mm. Okay, I've faced this off. Very slightly longer by about 0.5 mm than it needs to be. So let's Let's get rid of a few of these bits so that I don't reassemble it with the wrong components. Okay, that spring and okay. .80. Yep, and that's pretty much 80.5 millimeters. I've got a dial test indicator, a 0.01 mil. What's that? 5 thou gauge, and I've set it so that we are due. It's not a very accurate stand, so I can't get it exactly to 0, but there we go. That is pretty even across the whole width of the anvil. So let's pressurize it. That looks pretty repeatable to me. Yeah. That is a phono socket. So what we're going to do is just flatten a spot off and tap that into the side so that we can wire in this probe. That's why we used a circuit board, because there we go, that a circuit board, the spring is steel, obviously the pin is steel, so the spring will sit like that. Actually, let's do that. The spring will sit like that. So all we need to do is connect a wire from the centre, or anywhere in the middle of that pad, to the centre of this, and it will automatically fit in with the I've used phono plugs for my touch probes. So let's go and put this, oh blimey, yeah, it's okay. Let's go and put this in the mill, flatten a section off, drill, tap and put this in. There we go. I only have the plug tap for this size, so that should be absolutely spiffy. Oh, yep, he's cleaning that a little bit. That will tap. That will go in there a treat. I think I'm going to dismantle this and put it through the chemical blackening. An hour later, that came out okay. Good enough for this anyway. Right, so let's put it together and try it out. Right, here's a very simple way to use this this touch probe. Plug that into there, and now whenever I touch this probe on the mill, it digitizes. it triggers the digitized input. So all we need to know is the height of this, which I have already measured with the approximeters. 80.15 when it's fully done up. Take my word for it. So I've loaded the Hoss probing, offsets and probing. I've entered here, this is the thickness or the height of our gauge, which is 80.15, and I'm set up. I've just where the mill table happens to be, I've just reset it so that you can see what's going on. If I press the Z down button, it will drive the head down until it makes contact with our probe. That green light will flash, and it will drive the head back up, and it will zero this, zero the Z at the right height. So let's do that. Here we go. There we go. It's driving the head down. Driving the head down. Made connection, and it's gone back up. There you go. So if I go to toolbar, MDI, if I go G0 Z 90.15, it should stop 10 millimeters exactly above the top of our part. So let's try that. Here is a parallel, a 10 millimeter parallel. That just slides in there. So I think we can say that works. Okay. So the mill, or Mach 3, now thinks that this, the register face of the spindle, is, when it touches this probe, is 80.15 millimeters above the table, which it is. So now we've set that as the 0. So now we can drive the head up, put a tool in, come back down until we touch that. Then we'll be able to know exactly the length of that tool. This is tool 7, so I'll just enter that. You see it's brought up an offset because I'm repeating the same test that we've done before. Right, so if I now repeat the same test, we know the thickness of the, or the height of the gauge. So hitting this should drive the mill head down until it touches, resets, goes back up, and that is the actual height of the tool. So I could measure that, I could confirm that. I reckon that's 68.18. The probe reckons it's 68.13. So one of us is going to be closer. I think the mill is better. So all you do is then just keep putting your various tools in the mill, measuring the height of them, and then store them in the tool table within Mach 3. So every tool that comes off my my tool palette has got a number associated with it, because I numbered all the holes. I haven't numbered these yet because I might end up replacing them with better ones, but each one, so this is tool 7, as I said before. This, we know the height of this tool above the workpiece. That's stored in the tool table along with the other 20 odd tools, and also the diameter is, you store the diameter too. So very, very useful. Quite a reasonably quick way of using one of these. I hope that's been helpful to you. When I'd finished doing that, I thought, well, actually this thing is pretty redundant now, so so I made another piece. This is a tool holder adapter, so it's a pretty accurate fit. Fits on like so. You do the grub screws up to hold it in place, then you can put it in there, and you can use it as a touch probe. However, I wouldn't use it to find the edge of something, because I've had variable results with finding the edge. If your connections aren't absolutely spiffy on this, and Mach 3 doesn't pick up the fact that it's just collided with the work, you will have a crash. You'll break something, generally the probe. But because this is sprung loaded in the vertical direction, Z, it's absolutely ideal at finding the height of a workpiece. So it's relatively quick to put in. You can touch off on the top surface of a piece really easily. Very useful. Don't use it that often, but that's because you really need a proper kinematic probe, like a Renishaw. And I have been working on such a beast, but in fact I have got one that I made I don't know where it is now, I made some time ago, and it was pretty useless. So I didn't design it very well, and I didn't make it even worse. So yeah, a proper kinematic probe is the way to go. This is a sort of a good stopgap, and it's ideal as a tool setting gauge. And I made this one so that it doesn't bolt to the table, because this is such a small mill. I don't have any spare real estate on the table, so having a portable unit that you can just plonk on the table anywhere, use it, and then discard it when you're finished, and have all of the available table, is a better option for me. Anyway, I hope you enjoyed that. It's been quite a useful little thing to make. If you like the sort of rubbish I make, then please subscribe and hit that little bell button that'll tell you when I load videos, because I'm a bit sporadic with how often I can get them up. Anyway, take care and see you next time. Bye bye.